Okay, working with a graph to help us this time, they ask about the limit of a function, and this function has two sections to it. When x is less than 1, it behaves like a parabola. And if you extended this parabola, it would do something like that and curve in both directions. But they're saying it only behaves like a parabola when we're to the left of 1. When we're to the right of 1, it behaves like 3 minus x, which is a straight line going down like so. This is what's called a piecewise function because it's broken into a couple of pieces. Sometimes those pieces match up. Sometimes, like in this case, they do not, and there's a jump from one piece to the next. And they ask us about the limit as x goes to 1. So if we come at 1, there are two ways you can do a limit at 1. You can come at 1 from the left, so your numbers are going 0.7, 0.8, 0.9, 0.99, 0.999, getting extremely close to 1 from below. If you do that, because you're talking about numbers smaller than 1, this parabola is the function you should be paying attention to. We want to take x squared minus 2x plus 1 and say, how would this behave as x goes to 1? Well, we can put 1 into it, and we get 1 squared minus 2 times 1 plus 1, which is 1 minus 2 plus 1, which is 0, which tells us this section of the graph has the limit 0. It gets closer and closer to 0 as you sneak up on 1 here. And so we say, sometimes we write LHL for left-hand limit equals 0, or the formal way is to say the limit as x approaches 1, and then you put a minus to the right of it, meaning as x approaches 1 from the lower side, from the negative side of f of x equals 0. Now, what if we come in from the other direction? If we're talking about x going 1.3, 1.2, 1.1, 1.01, 1.001, we're coming in from the right side, from above, and now this section, the 3 minus x, describes our function. This is what we must pay attention to. And if we're doing this, we do 3 minus x. We plug 1 into it and hope that it works, and it works fine. And it tells us from the right, this function approaches 2. In fact, it actually reaches the point 1 comma 2 if you let it go long enough. So we'd say the right-hand limit equals 2, or in detail, the limit as x approaches 1 from the right, or from the positive side of this function, equals 2. The way I was taught to think of this is each of these functions is like a surface, and imagine a person walking along each one of these and getting closer and closer to the edge. As this person creeps up closer and closer, they walk up until their toes are hanging over the edge of this function, and you ask them what their height is, or what they think their height would be if they took one more tiny little creep to the right. This person would say that they're approaching 0. Right now they're at 0.0001, and they know that they'd reach 0 if they crept a little further. Over on this side is another person who came in from the right. They're standing on this ledge. They've been watching their y's go 0, 1, 1.5, 1.8, 1.9, 1.99, 1.999. They would say, if I crept a little more to the left, I think I'd land on 2. So that's the value of those two limits. The left-hand limit is 0, the right-hand limit is 2. Now, what they asked for wasn't the limit from the left or right. They asked about what's called the two-sided limit, the one that doesn't have any plus or minus on it. And the two-sided limit, the limit with no direction on it, here's the rule. This only exists if these two people agree. In other words, you only have the limit if the left-hand limit is the same as the right-hand limit. Otherwise, you don't. So in this example, our left-hand limit is 0, our right-hand limit is 2, and that means we have to say that the two-sided limit, the limit as f of x goes to 1, does not exist. It only exists if these two people come up with the same number. If he says, I think it's going to to 0 and he says, yeah, I agree, it's also going to 0, then you can say this limit is 0. But if the numbers are different, then you're done. This limit doesn't exist.